Visual Learning and the Study of Motion. 3, 2, 1, and liftoff. Discovery clears the tower. From the space shuttle leaving Earth's atmosphere to orbit the Earth, to a plane traveling from one continent to another, a car from one city to the next, or just people walking or throwing a ball, motion is part of our everyday life. Students have experiences with motion from the time they are born. So why, when they begin to study physics and physical science in school, do they have so many difficulties with the concepts? To help answer this question, I examined 6 different articles dealing with student understanding of forces and motion. After reading the articles, I settled on 4 which seemed to address the topic thoroughly. The first was students' understanding of the velocity time graphs and the source of conceptual difficulties. The second was Aristotle is Not Dead, student understanding of trajectory motion. The third paper was investigation of student understanding of the concept of velocity in one dimension. And the fourth and final paper was investigation of student understanding of the concept of acceleration in one dimension. The first article I will discuss is students' understanding of the velocity time graphs and the sources of conceptual difficulties. This study, completed by Natasha Ursig and Evisa Avania, was designed to investigate students' ability to translate the velocity time graph into a real physical situation. Then, to look at the possible sources of conceptual difficulties that students encountered. The graph on this slide is a sample velocity time graph, with velocity on the y-axis, time on the x-axis. The graph shows how the velocity changes with time. Drawing and interpreting graphs are the most basic skills of a scientist. Graphs provide quick overviews of major trend, and they detail irregularities within data. However, compared with scientists and experts, students' ability to construct and use graphic representations is reduced. Many student difficulties in solving kinematic problems arise from the inability to interpret graphs. In order to be able to use graphs, there are many things a student should be able to do. They should be able to select and determine the features of a graph that contain relevant information. They should be able to identify the relationship between different graphs, to show real physical systems graphically, to visualize a system based on its graphical representation. It seems as if students have a couple major difficulties when interpreting graphs. First is they do not know how to apply their mathematical experience and knowledge to graphs. Even though they have the basic mathematical knowledge they need, they seem to lose the ability when working with a graph. They have trouble getting the information they need from the slope or the height, and they misinterpret the changes in slope and height. Another group of difficulties students have is they have the inability to connect the graph with the corresponding objects and events in the real world. For example, they don't represent continuous motion by a continuous line. Instead, they seem to plot a number of unconnected points. The main goal of this study is to figure out the sources and the causes of the student's difficulty, and then to answer the questions, how can these be overcome? The graph pictured on this slide was the main graph used in the study. Students were to describe the changes in the velocity of a billiard ball during the first second, and then they were to explain what happened to the acceleration at the same time. The second question asks, why is the velocity change stepwise at the time 1.4 seconds? And what is the acceleration at that point? This study was conducted with high school students, and for most of the questions, less than 50% of the students had the correct answer. The study determined that there were three main reasons that students were experiencing difficulties. The first is that the physics textbooks contained many incomplete statements and did not adequately explain graphs or figures. The second is that the teachers showed a lack of knowledge of students' problem-solving strategies, and they overestimated what students knew. They seemed to show an inability to adapt their teaching strategy to the way students were thinking. And third was that students did not actually grasp what was happening physically, and so there was no way for them to understand the visual representation of the graph. The next two papers I read were written by the same authors and had very similar results and conclusions. The first was investigation of student understanding of the concept of velocity in one dimension. The researchers conducted the following two studies because many physics professors said that the same conceptual difficulties were occurring frequently and predictably among introductory physics students. In addition, the concept of motion is very important for understanding many future topics in physics. The researchers decided on a definition for student understanding. The definition is the degree to which an individual successfully applies the concept to the interpretation of simple motion of real objects. 4 groups of students participated in the experiment, in which they were to view actual physics demonstrations as well as visual representations and explain what was happening and answer questions. Students were consistently unable to determine if a ball was speeding up or slowing down. They also could not identify if there were instances where the 2 balls would have the same velocity or the same position along the track. If you look at the diagram to the right, it shows a sample question. Even though students could give an accurate definition of velocity, they could not explain the concept or understand what was happening in an actual physical representation. The implications for teaching from the researchers were that active intervention where misconceptions are actively targeted is necessary. They also believed that in order for students to gain these physical concepts, a satisfactory connection between the new concepts and the proto-concepts or experiences which the student has already had must be made. The second study, completed by David Trowbridge and Lillian McDermott, was the same basic study, except instead of working with velocity, they worked with acceleration. They had the same type task where students were asked to look at visual representations and explain what was happening and answer questions and problems about acceleration. In this example, taken from the study, students were supposed to look at the image and determine which ball has the greater acceleration on its sloping section. Consistently, students were unable to complete this task and continued to show many misconceptions with velocity and acceleration. In another example, students were to look at the question to the right and explain what the acceleration is at the top of the ramp. Again, students were unable to answer this question with any degree of accuracy. A significant number of students from the courses confuse the concepts of velocity and acceleration, and even after instruction, fewer than half the students demonstrated quantitative or qualitative understanding of acceleration. The researchers suggest that new curricular materials should be designed to help students gain basic understanding about velocity and instruction. The final study I explored was Aristotle is Not Dead: Student Understanding of Trajectory Motion. The researcher, Robert Whittaker, says that students' understanding of motion is more Aristotelian than Newtonian, and he says that even today, every student of elementary physics has to struggle with the same errors and misconceptions which had to be overcome during the day of Aristotle. Some of the misconceptions this study pointed out were that students believe that a force is required to maintain an object in motion. They also believe that forces are needed to maintain motion in the horizontal direction for the speed of an object once it's released. Also, many students indicate confusion between speed, velocity, and acceleration. The conclusion reached is that although students do have experiences with the phenomena of position, velocity, and acceleration, that the full meaning of the concepts hasn't been assimilated into their cognitive structures. In order to grasp physics concepts, connections must be made between the new concepts and the experiences with which the student is familiar. So for implications in my own classroom, I first must realize that students do have a lot of misconceptions when it comes to motion. Their experiences do not necessarily translate into understanding. The problem is definitely greater than just being able to interpret graphs or other physics images. From the studies, it is evident that even when seeing the actual physical representation of the physics idea, the students do not understand what is happening and are unable to answer basic questions. So, when working with my students, one of the most important things is to slow down and give activities that actually let the students have the opportunity to experience firsthand the concepts of motion. Then, when visual images are given, again, there's the need to slow down, to point out the important aspects of the images, and help the students actually relate the images to what they've physically done and seen. All of the studies that I explored were conducted with high school or college age students. And if these students are struggling with the concepts involved with velocity and acceleration, then I have no doubt my own students are struggling even more. I need to make sure that I correlate and relate the things I'm teaching my students to the things they experience in everyday life. And I need to actively confront any misconceptions they may have. Motion is an exciting and challenging topic for many students. The visual representations can be complex, and as teachers, we must understand our students' problem-solving strategies. We must make sure the images we are using are clear and well explained, and we must relate what students are learning to their previous knowledge.